First, I will have a brief review of what we have learned last time. Last time, we mainly introduced a very important fluid property, viscosity. Viscosity is actually is a measure of the resistance to deformation, right? So the natural viscosity, the natural ability to resist the deformation, or the harder to deform, right? Viscosity, very important one. And we have dynamic viscosity and kinematic viscosity, and in which kinematic viscosity is equal to the dynamic viscosity divided by the density. And also, according to whether to consider the viscosity of the fluid, because sometimes because of the viscosity is too small, we just can ignore them. We regard them as ideal fluid, which means that we think the fluid is frictionless, have no viscosity. Sure, that's impossible. Every fluid, real fluid um, is viscous, but sometimes we just can assume them to be non-viscous, right? So we, according to whether we regard the viscosity, we account for the viscosity or not, the fluid can be classified into viscous flow, or we call real fluid, and non-viscous flow, non-frictionless flow, ideal fluid, right? And also the viscosity can be a constant, right? Can be a constant. We just regard it as a constant. It doesn't change with time. It doesn't change with the shear stress. We can just divide the fluid as Newtonian fluid, in which the viscosity is a constant, or non-Newtonian fluid in which the viscosity is not a constant, okay? And also, a very important thing is the shear stress. The shear stress is not proportional to the velocity magnitude. It doesn't mean that you got a large fluid velocity, you got a large shear stress. The shear stress actually is proportional to the velocity gradient. Okay, it's very important. It's proportional to the velocity gradient. That means the larger velocity gradient, the larger the shear stress. That's why near the solid boundary condition, we generally have a large shear stress. So we can call them wall shear stress. Okay, and so, sorry, I forgot to mention one thing. When we don't consider the fluid viscosity, the no slip boundary condition will not apply to the ideal fluid anymore. It will be slippery boundary condition. Okay, that's very important, because for real fluid, for viscous fluid, we have a very important boundary condition. That's no slip boundary condition. Because the fluid viscosity, the fluid will stick to the solid when they are in contact with the solid boundary. That means the relative velocity will be equal to zero. That's why when Newton do the experiment, the fixed this is a fixed boundary, and this plate is moving with velocity u, and so the fluid contact with the lower plate will equal to zero, and the fluid contact with the upper plate will have the fluid will have the velocity which is same as the plate. Okay, this is no slip boundary condition. However, if it's ideal fluid, it will be slippery or slipping boundary condition. That means the velocity this will equal to zero. We don't have the normal velocity because the fluid can't go into the solid. So, however, for the ideal fluid, we have tau, the tangential velocity doesn't equal to zero. Okay, so that's a big difference of the fluid, real fluid, and the ideal fluid. Okay, and also we have discussed what will happen to the viscosity when the temperature change. For example, when the temperature increase, the fluid viscosity, what will happen to the fluid viscosity? It depends on its liquid or the gas, because we know the fluid viscosity is actually the internal friction force between fluid layers, and it is decided by two factors: the molecular attraction forces and the momentum transfer because of the molecular motion, right? So for liquid, when the temperature increase, the fluid viscosity will decrease because the molecular attraction forces decrease with the temperature increase. However, for gas, because when temperature increase, the molecular motion will also increase. So temperature increase, molecular motion increase, and the momentum transfer increase will be more frequent. So the gas viscosity will also increase. Okay, this is what we talked about last week. And today we will continue to introduce surface tension in force. Surface tension, we have met it every day, and we know just like the water beading, and is actually the surface tension or the soap bubble. The kids really like to play soap bubble. Actually, it's also a phenomenon related to surface tension. And so, what is surface tension? What happened? Why there is surface tension force? Surface tension is actually due to the asymmetric cohesive forces acting on the molecules of a free surface. What does it mean? A free surface means there is an interface between a liquid and a gas. And so the interface, actually, generally speaking, if there is density in continuity, there is interface, there will be surface tension. And it is a microscopic manifestation of the molecular force. What happened there? For example, just like here, we have the fluid molecule. The fluid molecule, if within the fluid, and it will have the molecular attraction forces around. And this one, if we draw FBD, it will have the attraction forces by the molecules surrounding it, and it will be in balance. However, if it's in the free surface, and definitely it still will have the attraction forces by the fluid molecule. It will also have the it also have the molecular force by the gas, right? We know that the molecular force for the gas is very, very small. It's like literally small, because the gas molecules, they distance between gas molecules are just large. Okay, so generally this molecular force by the gas can be ignored. And you see here, when we draw FBD, according to Newton's second law, that this molecular is actually in balance, it will have the resultant force. The resultant force will go inward, right? And so with this unbalanced force and go inward, and so the fluid, the interface, will try to shrink, and so this is the surface tension force. Okay, this force or symmetry actually resulting the membrane around the surface. Okay, so surface tension is actually surface tension force. Okay, and surface tension force, we use sigma to indicate surface tension force, and it's unit is Newton per second per meter because it's the force per unit length. Okay, so surface tension force is actually the apparent interfacial tensile stress that acts wherever there is a density discontinuity between a liquid and another liquid and a gas, liquid and solid. We just take example here. Take example as the interface between liquid and gas. It's much easier to show it, okay, to explain it. And sure, the surface tension can change with temperature. Just for example, for the water and air, the interface, the surface tension force decrease um, with the temperature. This can be is easy to understood, right? Because with the increase of the temperature, the molecular distance between water molecules will increase. So the molecular force, the molecular attraction force, the internal molecular attraction force will decrease, right? So this can be uh, easily understood. Okay, let's go. What happened here? Oh, sorry, I forgot to record. Okay, I forgot to record. I just need to record. Okay, continuous surface tension force. Okay, because I just start to record, I need to repeat surface tension. Sorry, just don't know what happened. Let's. Okay, not basically. Okay, first thing we need to understand surface tension force is due to the asymmetrical cohesive forces acting on the molecules of a free surface. We just took this example, and for the internal molecules, the forces are balanced, okay? It's in equilibrium. However, for the molecules near the interface, the attraction force by the fluid will be much larger than the attraction force by the gas molecules. So the molecules, molecular in the interface will try to will have invert will have an invert force, a resultant force, right? And so the membrane will try to shrink. Okay, this is the surface tension force. And if wherever there is a density discontinuity, there will be surface tension force. Why? Because if there is density discontinuity, so the attraction forces by different molecules will be different. So the resultant force will not be zero. Okay, so the force system will be unbalanced. That's why there will be surface tension force. One more thing is the surface tension force. Surface tension force is actually the force per unit length. So we use sigma to indicate the surface tension force, and its unit is Newton per meter. Okay, the surface tension force will will decrease by the increase of the temperature. Why? Because with the increase, just like here for the water, air, the interface, because with the increase of the temperature, the molecular distance will increase, the molecular force by the water molecule will decrease. That's why the surface tension force will also decrease. Okay, and for the surface tension force, we know its magnitude, but also it's very important about its direction. The direction of surface tension is always tangent to the liquid surface, right? The direction of surface tension is always tangent to the liquid surface and particular to the dividing lines on the liquid surface. For example, if this Mn is the dividing line on the liquid surface, just for example, I think if this is, we place soap bubble, this is a bubble, and we have this um, uh, uh, and this is a bubble. And so the force, the surface tension force, well, this is a dividing line of the tube interface, and so the surface tension force will always um, um, perpendicular to the dividing line, and it's tangent to the liquid surface, right? And so if we play this, let's show this. So I just forgot to if there is a small slope, okay, and I cut it, or the bubble, I just use a pin to break the bubble, and then the slope will go like this way, because the tension base will pull uh, the slope to this direction. Okay, so this is the surface tension force. Okay, you see, this is the liquid surface, and then this is the liquid surface, and so the surface tension force will tangent to the surface. And this is the dividing lines and the liquid surface, so it will be perpendicular to the dividing line. Because surface tension force is only a brief introduction, so we don't need to go deeper into it, but I would like you uh, to know some of them. This is a raindrop, okay? This is a raindrop, or you just can regard it as a soap bubble. And so when we cut it in the soap bubble into half, we will say the surface in the um, in the boundary in the interface. This is the interface, right? This is the interface, the convergential line will be the interface. So the surface tension force will perpendicular to the liquid surface. The liquid surface is the soap bubble free surface, and perpendicular to the dividing line. So this will be perpendicular to the dividing line. Okay, this is the direction of the surface tension force. And also for this one we'll introduce later on. This is capillary effect. For this capillary effect, this is just like the water column, and then the surface tension force, again, the surface tension force will perpendicular to tangent to the surface, and perpendicular to the dividing line. The perpendicular to the dividing line. Dividing line is actually again the circumferential line. Okay, so this is the surface tension force. This is surface tension force. Okay, so first you need to know why there is surface tension, and then one more thing, you need to know the direction of the surface tension force. Okay, and we give an example. The forces on half a fluid drop. The pressure inside a drop of fluid can be calculated using the FBD we have learned in theoretical mechanics. Um, this is a soap bubble, or this is a wind drop. You can regard it both, okay? And then if we cut it into half, and we can draw FBD, you see this will be the force due to surface tension, the force due to surface tension, right? The force due to surface tension will act on the dividing line and perpendicular to the surface. we're tangent to the service, we're tangent to the service and perpendicular to the dividing line. And this is the service forces due to surface tension, and this is forces due to inside air pressure. Okay, and we have the inside air pressure, also have the outside air pressure, right? And so according to the projection in the z-axis, we will have this. This is sigma is the surface tension force. It's force per unit length. So times the circumferential length will be the total surface tension force. And then this one is the area, the projection area by the pressure difference between the inside and the outside air pressure. dP includes the pressure difference between inside and outside. And we can find this, the pressure difference between inside and outside will be equal to 2 sigma divided by R. What does it mean? First, so this one is a little bit, you need to, there are 4 bubbles. Oh, there are 4 bubbles. What do you mean there are 4 bubbles? Here we just analyze one bubble and then we will see it later. Okay, the first thing you need to know is there is pressure difference between the bubble inside and outside. This is same because there is surface tension force. The second thing you need to know is the inside pressure is larger than the outside pressure, right? The inside pressure is larger than the outside pressure. And the third thing you need to know that the pressure difference increase when the bubble diameter or the bubble radius decrease. That means the smaller the bubble, the inside pressure is actually larger. Okay, this one, because we, for this part, for the surface tension force, it's just a brief introduction. There is actually a specific course for this surface tension force. If you want to do research in surface tension force, you need to know more here. No more later on, but here is just a brief introduction. Okay, so but one thing just for us, we should have the common knowledge for a soap bubble, for a raindrop, the smaller the inside pressure is actually larger than the outside. Outside is the air pressure, right? Is atmospheric pressure. Okay. Oh, no, DP is not. Oh, it is a 4 bubbles. You mean if there are 4 bubbles? No, they are not. The sigma, the surface tension is decided by the need by the materials. Okay, by the water, air, or just water, just. For other liquid, okay, the sigma, if for the bubble in the air, for the soap bubble in air, sigma is equal for the 4 bubbles. But R, the radius for each bubble, if R for the radius for each bubble is different, so dP will be different, right? Because for each bubble, you can draw FBD. We call what you have learned in theoretical mechanics. And the pressure difference will be different. The pressure difference is decided by the bubble radius and decided by sigma surface tension. Okay. And here, for example, we have we this have this mechanism. So we have two bubbles. We have two bubbles here. One is small, one is large. So what will happen just after a time, the small bubble will become large, the large bubble will become small. Finally, they are equal. Or the small bubble will be smaller, 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 and the large bubble will become larger, larger, larger. Can you tell me? Can you tell me what happened here? Here we see we use delta B equal to 4 sigma r instead of 2 sigma r. I need to explain them because for us here for the soap bubble we got it as just thin enough. We don't have actually for soap bubble should be like this. We have the inner wall, inner membrane and outer membrane. Okay, we have this. Okay, so here we have the pressure difference. So why there is 2 sigma and the 4 sigma is decided by whether you consider the thickness of the membrane or not. If you don't consider the membrane as thickness, it will be 2 sigma. If you consider the thickness of the membrane, it will be 4 sigma. Okay, so we don't go into detail, but we know that the inside pressure is larger than the atmospheric pressure, the inside pressure of the bubble. And the smaller the bubble, the larger the inside pressure. So, can you tell me what will happen to these two bubbles? Will the small bubble increase its size and the large bubble decrease its size, and finally they will become equal size? Or the smaller bubble will decrease and finally disappear, and the large bubble will become larger. Which one? Can you guess? Can you tell me? Can you tell me smaller bubble become increase? You mean they become equal? You think? Really? We always say in real life, the richer, the rich people become richer, right? The poor people will be poor, right? In China, we always say this. I don't know what happened in your country. We always say, if you are rich, and you will become rich and rich, you will have more money. But if you are poor, you will be poor and poor. Why? It also happens here. So that's what I always tell my Chinese students. In the study of mechanics, you will know what happened to your life. This also applies. Why? Because for the smaller bubble, actually, the larger the inside pressure, that means for this small bubble, we have P in P1, and this is atmospheric pressure. This is P, we use PS to indicate small, okay. This is big, this is PA. We know according to what we have analyzed, because of the surface tension force, PS is larger than the atmospheric pressure, is larger than the air pressure and then the inside pressure of the big bubble. That means P S is larger than PB. And so we know fluid will flow from larger pressure to lower pressure, right? I think it's common sense, right? The fluid flows from this is the pressure will decrease uh, along the fluid direction, right? This one we should know this, right? So you will say later on, PS, for this one smaller, and this larger. Never think that people will become equal. No, that will not happen. If you are rich, you got more chances to become much richer. Okay. If you are poor, you have less chances. Okay. So that's what happened. Okay. So I think this one can help you to memorize. Okay. The inside pressure is larger than the atmospherical pressure because of the surface tension force. Because surface tension force try to pull the surface tension try to be shrink. And also one more thing I want to ask you for the raindrop, or just like this one. This one is almost spherical, right? This one is almost spherical, but it is not really spherical. Why? Because because of what? Because of the gravity force. If you go to the airspace, the water bed will be a real spherical. Okay. So we just talk about the surface tension force for water and air, okay, for soap bubble. But how about if there is a liquid, gas, solid surface, just like this is liquid, this is solid, and this gas. And then we will say for, again, the molecular forces, you can just analyze this easily, use molecular forces. So definitely the solid molecules will attract the liquid molecules, right? And the liquid molecules will have the attractive force by other liquid molecules. And also for the membrane, for this, again, we will have the surface tension force, right? We know this already. This is just like this is water, this is air, right? We know this surface tension force, right? The membrane force, okay. And but if there is solid, what will happen? And sometimes we will say we will have the wetting. This one is wetting, and we have non-wetting, just like we have the wetting, we have non-wetting. Because if there is water, we drop a water on the soap, or we drop the water on the wax, it will be totally different. Why? Because here for the soap molecule have a larger attractive forces than the water molecules. So that means the soup will pull the water to them. But on the contrary, if the water dropped to the wax, the wax molecule force is smaller than the water molecule force. So the water molecule force, they win, okay, and so the water will shrink. Will try to be away the wax. So for this one, we just define them as wetting, and for the water wax, we define the non-wetting. And we also have the definition of the contact angle. So what is contact angle? Contact angle is actually the angle at which the liquid vapor interface meets the solid liquid interface. So this one will be the contact angle, okay? And the larger the contact angle, the higher the surface tension. So here for the water soup, the contact angle is smaller than 90 degrees. And so the water will spring to the soup. This is wetting. However, so very good. You just keep asking, contact angles are important to realize the materials wet or not, right? Ah, yeah, it's a very good question. Yes, the contact angle. So here I don't go into detail about the contact angle because it's just as I said again and again. It's just a brief introduction. And yes, the contact angle decide whether it's rating or non-rating. It's just like the soap just pull the water to itself. Here, the wax pushes the water. Okay, so generally speaking, the conductor angle is smaller or larger than 90 degree, but it happens sometimes they I don't know whether there is almost near to 90 degree. I don't know. I'm not so sure. Okay, but maybe you can check online. So maybe if the molecular forces they are equal, just like the molecular force by the solid is equal to the molecular force by the liquid, maybe there will be 90 degree. Okay. So for different liquids, let me check. Oh, the mixture of oil and water. The mixture of oil and water, you mean on the soup or on the wax? Because for different liquids on the same substrate, it will be different. Okay. Oh, yes, you got it. There is 90 degree. The contact angle is 90 degree. Okay. Just like here, the contact angle is 90 degree. Just for the same substrate, if the oil, we have different oil, and so it's totally waiting, right? And totally waiting, and we even can't, we see nothing here. And for the oil, this contact angle is almost is equal to zero. It's fully waiting, and it's actually go inside almost. We can see that. Okay, just as service. Okay, for this contact angle is smaller, is 30 degree is still rating, and then it start to increase. And finally, you will say when theta equal to 180 degree, and this one is totally non-rating. Okay, that is only maybe just the contact is not a surface, it's contact point. And this is for the different liquid and the same solid. And for the same liquid but different solid, we say different substrates. Okay, it's actually different solid. Even the same liquid, the contact angle is totally different. Okay, again we got theta equal to 90 degree. Okay, so this one, okay, they have the equal molecular forces. Okay, and you see the contact angle, this is rating. Yeah, we can see this. This is the solid just push the liquid to itself. And this one is actually liquid try to pull them away from the solid. Okay, this is non-wetting. And so for the soap is actually wetting, right? That's why we can wash our clothes. Okay. So one more thing about the surface tension is capillary effects. Okay, are very a common phenomenon we just have seen in daily life is the um, capillary effect. Just for this, the tube is open. The tube is open. So if the tube is open, according to what you have learned before, what should it be? If the tube is open, the level, the water level, the inside of the tube, the water level should be equal to the free surface outside or not. For here, if the tube is open, generally we think inside and outside should be the same, right? The interface should be the same, right? Because here is air pressure, atmospheric pressure, and here is also atmospheric pressure, right? This is what we have learned before, right? But what happened when the tube diameter became smaller and smaller? What will happen? In daily life, you will find this. When you drink tea, when you drink milk, you use a straw tube to drink the milk or drink the water. When you get smaller and smaller tube, at the beginning, inside and outside, they should be the same, the water level. That's for sure, because the atmospheric pressure outside and inside, okay. But when the diameter decreased, we'll find that inside the tube, the water level will start to rise about the water level outside the tube. Okay. Yes, liquid will increase. But what happened here? You see, if here is atmospheric pressure, PA, and we will do the FBD. This is PA, and this is PA, and this water column weight, the weight of the water column, you see, we will have, sorry, according to what we have learned in middle school, we will say this. This is PA. And this, if we just assume there is a very thin plate here, this is PA, it's imbalance. And so we have the weight, right? We should have PA times the area plus the weight of the water column equal to PA times the area. That's impossible. So what happened here? Actually, oh, sorry, we use the here. Actually, this is the weight of the water column, and we have this surface tension force to balance the water weight. Because of the surface tension force, that's why the water level increase inside the tube. Okay. And we can find out the head edge is governed by the value of the surface tension and the weight tube radius and specific weight of the liquid and the angle of contact. we can use this FBD and then we can widen the equilibrium equation in vertical direction. And this is here should be delta P. Okay, here should be delta P. Okay, inside this is the outside. This is inside. This is delta pressure difference. Okay, times the area it acts, and this will be the surface tension force. I don't need you to. This is actually the according to the FBD. You just write down the equilibrium equation in vertical direction. Okay, and finally you will have this. You will have this formula. What does it mean? If sigma gamma cos theta is equal, that means if the same liquid, okay, same solid tube, so the head of the water column inside the tube will be inversely proportional to the tube radius. That means if the tube diameter decrease, the water level will increase, just like here. You see, the decrease diameter left, right, and the water level increase. Okay. Okay, so this is the capillary rise. Okay, so let's take 10 minutes break and then continue. Okay. So height of the liquid depends on only its radius, the angle. No, not only if, I mean only if the same liquid, same tube material. Here, just like oil or the water or just the milk, you just use the glass, okay? Now, so here, this time, the water level will be only decided by the tube radius. And the smaller the tube radius, the higher the water level. However, if you just change the, the oil to the milk to the water, they will have different surface tension force, just like here. Sorry. You see, the height is decided by the surface tension and you also decided by the contact angle. We know just now I have shown you the contact angle is decided by the liquid by the solid. The same liquid but different solid, we will have different contact angle. Same solid, same substrate, different liquid will also it will also result in different contact angle. So here I only talk about when we have the same fluid, same liquid, that means sigma, contact angle, and spectral rate are all equal to each other. Okay. So this time H will be only decided by the tube radius and is inversely proportional, okay, to the tube radius. Okay, we will talk to later. Okay, 10 minutes break and then we'll continue.